Welcome to The Explainer. Today we're going to tackle one of the absolute most vital mysteries in modern technology, and that's the mystery of machine learning and fairness. Now, we often just kind of assume that computers are perfectly logical, perfectly impartial judges, right? But as we're going to uncover today, the reality is a whole lot more complex and honestly way more fascinating.
Okay, let's dive into this. Are algorithms truly objective? Because we really think of artificial intelligence as this cold, calculating, neutral entity. But think about it. What if the data we actually feed into these algorithms is already poisoned from the start? We really need to shatter that illusion of the perfectly objective machine right now.
Consider this university admissions case study. So during testing, a model might score exceptionally well. It's hitting high overall accuracy and precision. Basically, it looks totally perfect. But the alarming reality when you actually deploy the thing reveals a completely different story. It turns out qualified students in the majority demographic group were being admitted at nearly twice the rate of equally qualified minority students. So how on earth does a supposedly highly accurate model become so incredibly biased?
Well, here's our roadmap to figure that out. We're going to debunk the myth of objective AI, track down exactly where these biases lurk, learn how to mitigate them, and then finally, evaluate models using three very distinct mathematical definitions of fairness.
Section 1. Where bias lurks, finding the source. To fix that broken admissions model, we absolutely cannot just look at the code. We've got to look at the human behaviors that pollute the training data way before the algorithm ever even sees it.
First step is what we call historical bias. This happens when our data simply reflects the inequities that were already baked into the world at the time it was collected. I mean, if you train an admissions model on 20 years of past student records, or say train a real estate model on 1960s housing data, you might literally just be teaching the machine how to reliably replicate past human discrimination.
Then there's automation bias. This is our very human tendency to favor automated systems over human judgment. Imagine a factory where a computer model looks for defects in sprockets. A supervisor there might just blindly trust the computer's output, even if its actual precision is, say, 15% lower than human inspectors. Going back to our admissions case, the committee probably just trusted the algorithm blindly simply because, well, it was a computer.
Now, what's really interesting about this is how our own social circles unconsciously bleed into our data. Take in-group bias. The computer science students who actually built that admissions model might unconsciously favor applicants coming from their own specific CS academy. And then on the flip side, you have out-group homogeneity bias. That's where they might stereotype all non-academy applicants as unqualified, just because they don't share that exact same background.
We also definitely have to watch out for confirmation bias. This is when developers unconsciously process data in ways that just affirm their pre-existing beliefs. Let's say a programmer had a completely traumatizing childhood encounter with a hyperactive toy poodle. They might unconsciously discard data proving small dogs can be docile when they're curating a dog adoptability model. Their own personal, deeply held beliefs literally alter what the machine learning model spits out.
Section 2. Mitigating bias. Fixing the data. So now that we've established human nature is super messy, how do developers actually play detective and find these hidden biases lurking deep inside their massive spreadsheets?
When developers are scrubbing data, they're looking for some pretty glaring errors. Take a look at the Labrador Retriever listed here as being 35 years old. Now, this is what we call an unexpected feature value, and it's a massive, massive red flag. A 35-year-old dog is biologically impossible, right? So that tells us there are serious data collection or recording errors happening that are absolutely going to introduce major bias if we just leave them unchecked.
Beyond those wild unexpected values, developers are scrubbing their data for missing feature values and data skew. And you've really got to remember, missing data isn't always just random. For example, if temperament data is entirely missing for dogs rescued from big cities, that missing data might actually act as a proxy for small dog breeds, which are obviously far more common in urban environments. Because of that, your model will silently learn to be a lot less accurate for small city dogs. Okay, so once we actually find the bias, how do we mitigate it? There are two main solutions. Step 1 is the most straightforward. You augment the training data by collecting more diverse examples. But honestly, gathering more data isn't always legally, financially, or practically possible. So when you can't just get more data, you move to step 2. That's where you adjust the model's optimization function to mathematically penalize the system whenever it makes fairness errors during its training.
Let's break down a couple of the advanced mathematical tools developers use to enforce fairness right inside that optimization function. We have MinDiff, which basically balances error distributions across entire slices of data. So it would penalize the model if its prediction errors for male students were vastly different than for non-binary students. And then we have counterfactual logic pairing, or CLP, which tackles things at the individual level. It makes sure that if you change just one sensitive attribute, like gender, the final prediction for that specific individual example stays exactly the same.
Let's move to Section 3 and see how this builds into evaluating fairness and improving the model. We've cleaned our data, we've tuned our optimization functions, but how do we actually prove, mathematically, that our newly fixed model is fair before we release it out into the wild?
This brings us right back to a massive structural challenge. If overall accuracy can so easily hide bias against minority groups, how do you even go about choosing the right metric for fairness? Remember our university admissions anchor? The committee was totally thrilled with a 90% overall accuracy score, but that high overall score meant absolutely nothing because the subgroup accuracy for minorities was incredibly skewed.
So the first major metric we can use is called demographic parity. This stipulates that the admissions rate should be exactly the same across all demographic groups. The goal here is pretty simple. Ensure the admitted class perfectly mirrors the proportions of the original applicant pool, completely without looking at individual qualifications.
Under demographic parity, if the model accepts 20% of the candidates from the majority group, it absolutely must also accept exactly 20% of the candidates from the minority group. It creates a perfectly mathematically balanced representation across the board.
But here is the gotcha moment. Demographic parity completely ignores the underlying distribution of predictions, meaning it ignores who is actually qualified. What if, just within the specific applicant pool, the majority group happens to have a much higher number of truly highly credentialed, qualified candidates? If you force a flat 20% acceptance rate for everybody, the highly qualified group sees their acceptance rate just plummet. And that feels deeply unfair to those individuals who worked so hard for their credentials.
To solve that flaw, we introduce our second metric, equality of opportunity. Now, this metric shifts the focus away from everyone and places it strictly onto the qualified pool. It ensures that students who actually possess the preferred label, meaning they're flagged as qualified, have an exactly equal chance of admission, entirely regardless of what demographic group they happen to belong to.
So now, instead of just a flat overall rate, the model accepts exactly 40% of the qualified candidates from the majority group and 40% of the qualified candidates from the minority group. Now, sure, the overall acceptance rates might look unbalanced to someone on the outside, but arguably, this is a much fairer outcome for a university that is specifically seeking to admit top talent in an equitable way.
But let me throw a huge wrench into this whole narrative. What if 94% of our applicants completely opted out of reporting their demographic data in the first place? We literally cannot calculate demographic parity or equality of opportunity because we simply don't have the demographic labels to group the students together.
And this brilliantly illustrates our third metric, counterfactual fairness. Even with only 6% of the demographic data known, we can still test the model. We do this by taking two identically credentialed individuals who differ only by a sensitive attribute, like their demographic group, and we compare them side by side. If the model accepts the majority candidate but rejects the identically qualified minority candidate, it flat out fails the counterfactual fairness test at the individual level.
So, the absolutely crucial takeaway here is that we now have three distinct mathematical definitions of fairness: demographic parity, equality of opportunity, and counterfactual fairness. But here is the fascinating and maybe slightly terrifying truth. Mathematically speaking, these definitions are often mutually incompatible. You literally cannot satisfy all of them at the exact same time for a given model's predictions. Which leaves us with a final, pretty provocative question. If our mathematical definitions of fairness are mutually incompatible, is true universal fairness in AI actually mathematically possible at all? As we keep designing the future of machine learning, we really have to realize that choosing the right fairness metric isn't just some cold engineering decision. It requires understanding the context, understanding the goals, and ultimately it is a deeply human choice. Thank you so much for joining me on this explainer. Keep asking those hard questions and keep exploring the data.